Hi, my name is Rachel, and today I'll be talking about a paper I wrote with Meghal Gupta called The Optimal Error Resilience of Interactive Communication over Binary Channels. So to begin, I want to review the notion of an error correcting code. Consider the task, the following scenario where Alice, represented with this pink dot over here, has an input X which she wants to send to Bob. However, the channel over which they are communicating is noisy. So the question is like, how can they do this so that Bob can learn Alice's original message X? So for today, our channel is made noisy, which means that there's going to be either errors or erasures happening. Errors are simply bit flips. You take a bit and you replace it by the other bit. And erasures are you take a bit and you erase it, and then instead you have an empty slot saying that there was a bit here, but you don't know what it was. So of course, Alice could just send her message X to Bob in the clear. However, if there are any bit flips or any erasures, then suddenly Bob can no longer figure out what her message actually was supposed to be. So instead, she sends an error correcting code of X, which will have some properties such that as Bob can still determine what the original message was, as long as there aren't too many errors or erasures that happened. So more precisely, an error correcting code is a family of maps, and it has relative distance delta if for all X not equal to Y, the Hamming distance between the encodings of X and of Y is at least delta n, where n is like the length of the encodings. So relating this back to error erasure resilience, it turns out that delta relative distance implies that you can correct back to the original code word as long as there are fewer than delta n over 2 errors or delta n erasures. So over a large alphabet, there exists an error correcting code with relative distance 1, and over the binary alphabet, there exists an error correcting code with relative distance 1/2. So the problem we're going to be more interested in today is that of interactive coding. So in interactive coding, you start with original noiseless protocol. Here's pi naught, which consists of n naught rounds, and you want to convert it to an error resilient version of the same protocol, which we'll call pi. And pi can run in n rounds where n is not necessarily equal to n naught, and the messages will all belong to some alphabet sigma. And we say that pi is delta error or erasure resilient if for any errors or erasures of delta n of the rounds, Alice and Bob can still determine the original noiseless protocol. So I want to say a word about why this problem isn't just trivial. So like consider the following transformation. You have an original protocol pi naught, and you convert it to this following protocol pi prime, where every message you just send the error correcting code encoding of the message that was in the original protocol. And so the reason why this doesn't work is because the adversary is given a budget of like a constant fraction of the entire communication of pi prime, which means that they have more than enough communication or more enough budget to just corrupt the first message entirely. And now once the first message has been corrupted, the rest of the messages don't really make any sense. And because they'll, you're suddenly doing an entirely different protocol with entirely different first message. So you cannot simulate the original protocol pi naught. So the question, so in interactive coding, you have to make sure that you're able to sort of correct for earlier mistakes, even as you're trying to continue with your simulation of the protocol. So that was interactive coding. Interactive coding, you take a protocol and you convert it to another protocol. I wanted to mention another variant of error correction, which is interactive, called message exchange. So in the message exchange protocol, you have Alice has an input X and Bob has an input Y, and they just want to send their inputs to each other. And so the question is like, how can you simulate this, 2-round protocol, or 2-message protocol interactively so that it's error resilient? And I do want to mention that message exchange is like a subcategory of interactive coding, right? It's like, it is an interactive coding, like it is like an interactive protocol, but also that like any interactive protocol can be simulated by a message exchange or like computed by a message exchange with up to exponential blowup. Because you can just consider Alice and Bob, which have private inputs X and Y, and they can just send over their private inputs instead of running the interactive protocol. So there is like a little bit of loss of generality, but at the same time, it's a related problem to the problem of interactive protocols. So now let me talk about some past work. So let's first start with a large alphabet case. So I said earlier that error correcting codes have distance 1 over a large alphabet, which means that for errors, they're resilient to 1/2 errors and also to 1 fraction of erasures. So in the interactive setting, the two-way, two-party setting, you have 2 parties talking. So each one has to be resilient simultaneously. So you get a factor of like 1/2 as much resilience. So for interactive coding over errors over a large alphabet, Braverman and Rao showed that you cannot do better than 1/4, and you can also attain 1/4. And for erasures, you can, like the optimal is 1/2. Okay, so over the binary alphabet, error correcting codes can only have a relative distance of 1/2, which means that everything is sort of like cut in half, at least for error correcting codes. So in particular, for errors, you can be resilient to 1/4 errors, and for erasures, you can be resilient to 1/2 erasures. The interactive coding setting is a little bit more interesting. So it turns out that you can show that you can't do better than 1/6 for errors. And if you simply just replace every message of the Braverman-Rao protocol with like the large alphabet protocol with an error correcting code of that symbol over the binary alphabet, you can get an error resilience of 1/8. And a couple of years ago, these people showed that you can actually improve 1/8 to 539. But the actual optimal error resilience between 539 and 1/6 is what's an open problem. Similarly, for erasures, it was known that you can't do better than 1/2, and the best construction known beforehand was 1/3. And it was also unclear, like, can you do better than 1/3? Yeah. So in our paper, we resolved both of these problems. So we show that, in fact, you can attain the maximum like upper bound for both of the settings. So I do want to mention that our erasure protocol is in the interactive coding setting. So your simulated protocol is a constant multiplicative factor communication. Your communication of the erasure interactive coding protocol is a constant fraction larger than the original protocol. However, for our interactive coding protocol, our error resilient protocol for errors, we only achieve it for message exchange. So we don't achieve it for any arbitrary protocol. So I also want to mention that it was previously known how to achieve 1/6 error resilience if Alice and Bob are given the additional power of feedback. And what feedback means is that, say I send a message and I also get to learn instantly what was really the other side. So if there was an error, if the adversary corrupted it, I also get to know, like, what the receiving party received, which allows me to tailor my messages in the future to what I know they've seen so far. So I can basically give them the piece of information they need to hear at all points in time. So basically what we're showing here is that you actually don't need feedback to get the 1/6 error resilience. So somehow, like, even though feedback seems like it's like extremely strong power, you actually can do just as well without it. And as for the erasure setting, I think it's sort of interesting that we can get 1/2 because, like, it basically means there's no gap or no difference between using a large alphabet or using a binary alphabet, at least for interactive coding, which is a little surprising. It's like saying that the binary alphabet is like as powerful as large alphabets are. Okay, so out of the 2 results, I guess the 1/6 protocol is a more interesting one. So I'm going to be spending the rest of my time today talking about that. So let's talk about message exchange over the binary channel, resilient to 1/6 errors. So we begin with our message exchange protocol, where Alice sends Bob X and Bob sends Alice Y. And let's just consider like the simple transformation where they both send an encoding of their inputs. So as I said before, encoding codes over the binary alphabet have distance 1/2. And so you can be resilient to 1/4 of corruption of an error code. And since there's 2 directions and both parties have to learn the other person's input correctly, you get the total protocol is 1/8 error resilience. So each direction is resilient to 1/4 errors. So this isn't good enough. We're really aiming for 1/6. So we want to increase this number 1/4 to 1/3. So let's consider this like second idea. This is called the question answer approach. And so suppose that Alice is trying to learn what Bob's input was. So she's going to keep track of a guess y star for Bob's input. At first, it's going to be the empty string. And she's also going to keep track of a counter CA, originally set to 0. And this is going to sort of know how confident she is that this guess y star is actually the correct, it's actually Bob's correct input. So every round, Alice is going to send over the error coding code of y star, her guess. Bob is going to respond by sending over one of 4 instructions. So they basically mean 0 or 1 means you should add 0 or 1 to the end of your current guess. This like delete symbol, rewind symbol, means you should delete the last bit because that was wrong. And this bullet symbol means, oh, okay, good, you have the correct you have like y star is equal to y. Now start increasing your confidence. And the important point is that these 4 messages can be distance 2/3 apart, which is going to be very vital for us. So meanwhile, Alice, when she receives the bullet, she's going to increase her confidence by 1. Otherwise, if her confidence is actually 0 at the moment, she's going to either append the bit or delete the last bit according to the instruction. And if the confidence is greater than 0 and she receives either 0, 1, or 1, she's going to decrease her confidence. An important point is that for any bad instruction that Bob gives to Alice, that the adversary makes Bob give to Alice, then this can be corrected by 1 good instruction from Bob. So at the end of the day, as long as Alice has received n more correct instructions than wrong instructions, then she'll have y star equal to y. She'll know Bob's input. And so because the 4 so that means basically that the adversary has to correct every other of Bob's messages, so that she'll make like +1 progress and then like -1 progress. And so this is like 1/3 of Bob's messages overall, because his messages are distance 2/3 apart. So that's good. We have increased 1/4 to 1/3. However, this is only one directional, right? This is like only true. We only have 1/3 error resilience for Bob. And the question is like, can we get error resilience 1/3 for both parties simultaneously? So to do this, we're going to do simultaneous question and answering. So Alice is going to have a guess y star and a counter CA as before, and Bob's going to have his guess for Alice's input x as well as his counter CB. And so every message, Alice is going to send the error coding code of 3 things. So it's going to be, the first part here is going to be her question, so her guess of Bob's input. And the second part is going to be her answer part. So this is going to be the X question mark is going to be the question she thinks Bob just asked. So her guess for what Bob's guess for her input is. And sigma is going to be the instruction, so 0, 1, rewind, or bullet, for what Bob should do to this X question mark. And so similarly, Bob is going to send the encoding of his question X star along with his answer, which is going to be Y question mark and up to the instruction sigma. So, Bob will answer whatever question he thinks he has just received. It may or may not be Y star, but like, you know, if it is, then like obviously Alice should update according to that instruction. But if it's not, then like there's no reason for Alice to update because she knows a lot of corruptions. Like, you know, this like instruction sigma makes no sense. So we're going to say that Alice only updates her guess and her counter if the question that Bob is answering is actually equal to her question. So as before, we're going to need some properties of the error coding code just to guarantee that we can get distance 1/3, or like the error resilience 1/3. And so here are the conditions. So given any X star and Y question mark, the 4 instructions, 0, 1, rewind, and bullet have to be relative distance 2/3. And outside of this, every other pair of code words has to have relative distance 1/2. And we can show that you can construct this, and it's not too hard. So that's what our ECC is going to look like. Okay, So here's the issue though with this current construction. So it's possible for the adversary to corrupt Bob's answer. So if Bob could, so it's possible for the adversary to corrupt Bob's message so that Alice receives a different question x prime, which is not equal to Bob's actual question. But now the answer is of the form like her actual question and a wrong answer, a wrong instruction that had updated. It only takes 1/2 error because they're only 1/2 apart. And so now Alice is going to make a bad update. She can make -1 progress just with 1/2 error. And so the issue here is really that like it's too cheap, it's too easy for the adversary to cause Alice to make a bad update. So just to like see how this plays out in like an actual attack over many rounds. So if Alice receives this corrupted message with a false question, she's going to respond by asking her question again, along with the answer to this false question. And then Bob is going to send back another answer and this question again. And let's say it's not corrupted at all. So now Alice actually receives a good answer to her question, and she'll make a +1 update. And then let's say that Alice will continue to respond to this, and this will kind of go in a circle back to the original corrupted message. So what's happening is that the adversary can corrupt every other of Bob's messages to cause -1 progress, those messages for Alice, and then +1 progress every other message. So overall, there's going to be 0 progress, and the adversary only has to corrupt 1/4 of Bob's total messages, which is like kind of bad. So it seems like maybe you haven't really made progress because you can still corrupt 1/4 of Bob's messages and just cause nothing to happen. However, if we look a little closer at this attack, we'll see the following. So if we look at Bob's update, so for this first message here, so Alice is responding to an incorrect question. So Bob is going to update 0. However, for the second message here, Alice is actually going to respond to Bob's correct question. And so she's going to make +1 update. So even though Alice's progress is sort of stagnant at 0, Bob is making steady progress towards learning X. In fact, as this continues the entire protocol, he'll have learned X and be very, very confident in its correctness by the end of the protocol. And so there's sort of an imbalance here, right? Because like on one hand, Alice can make no progress, on the other hand, Bob can make like way too much progress. So the question is like, can we rebalance this protocol so that when Bob has learned the correct X, has X star equals X, it suddenly becomes harder to cause negative progress for Alice. So this way that Alice can also learn the Bob's value of Y. So here's how we're going to do rebalancing. So Alice's input is X, her guess is Y star, and her counter is A. So whenever she receives a message of the form X, so this is Bob's question, but it's also like, let's say it's also equal to her input, then she's going to update her guess and her counter with probability 1. But if she receives a code word where the question is not equal to her real message, then she's going to update with probability only 1/2. So returning to the before scenario, when Bob has learned X, so when X star equals X, then when he sends this like error having code of his question, which is equal to X, along with an answer for Alice, and the adversary decides to corrupt it to a different question X prime, along with like a false bad instruction for Alice, only -1/2 progress will be made instead of -1, which is like good for us. However, this like rebalancing has created sort of a new problem, which in the case that Bob doesn't actually know what X is. And in this case, it's possible for the adversary to corrupt Bob's message from X star, from like an incorrect, like a question that's not actually equal to Alice's message X, to a question where the question is X, along with like an answer with a bad instruction. And this will cause -1 update for Alice. So that's not good because now there's like too much negative progress in this case. But we're going to fix this by looking at the next message. So the next message from Alice is going to be of the form her question, along with her actual input, because that was equal to Bob's question that she received, along with a bullet. And so basically, if we could get this we could get Bob to make +1/2 update in this case, and it will average out to a -1/2 update overall, which will be like completely fine for us. So in particular, when Bob receives the error correcting code of some question along with some answer where the answer instruction is bullet, he's going to update his guess and counter to be closer to x prime with probability 1/2. And so this turns out to be basically enough to like complete the description of the protocol, and it turns out this will actually work if you do the analysis. I do want to mention that I've been talking the entire time as if the adversary can only corrupt entire messages, entire code words into other entire code words. But it's totally possible in practice for like the adversary to simply corrupt a few bits so that it's like not a code, like it's not any code word, it's like in between some code words. So basically what's going to happen there is like the parties are going to choose to round to a certain nearby code word with some probability dependent on the distance to that code word. And this will end up working out. And so when you do the analysis, the potential you want to use is, at least from Alice's perspective, is you want to look at Alice's progress plus the minimum of Bob's progress and the length of Y. And if you do all the analysis with this protocol description, then it will work. And I think that's it for me. So yes, I did not talk about the erasure protocol, and it's actually quite different than the 1.6 protocol. But it is a much simpler description, so I advise you, I guess, to check out the paper for that. We also have another talk on interactive error correcting codes, which will use some similar techniques to the erasure protocol. Okay, so thank you.